Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us first understand the key concept here. Acid-catalyzed dehydration of allylic benzylic alcohols and ring expansion via carbocation intermediates combined with the thermodynamic drive toward aromatic stabilization. Moving on to the next step. Identify the starting material. The compound is cyclopenta-2,4-DN1-YL methanol, a cyclopentadiene ring bearing a CH2 of substituent at the sp3 carbon C5 position between the two double bonds. Moving on to the next step. Protonation of the hydroxyl group under acidic conditions converts OF to OF2+, which is a good leaving group. Loss of water generates a carbocation at the exocyclic CH2+ position. And for the final step, this primary carbocation is actually stabilized because it is allylic homoaromatic relative to the cyclopentadienyl system. More importantly, the resulting CH2+ adjacent to the cyclopentadienyl system allows for a 1,2 hydride shift or ring expansion. Ring expansion mechanism: the exocyclic carbocation CH2+ is adjacent to the cyclopentadiene ring. A 1,2 carbon shift ring expansion occurs. The C-to-C bond of the ring migrates to the carbocation center, expanding the 5-membered ring to a 6-membered ring carbocation, cyclohexadienyl cation, i.e., the arenium cyclohexadienyl cation. The cyclohexadienyl cation loses a proton, H+, to restore aromaticity, yielding benzene, which is highly thermodynamically stable, aromatic. A methylene-cyclopentadiene would form if only simple dehydration occurred without ring expansion, but this is not the favored pathway under these conditions. C. Cyclohexadiene and D. Cyclohexene would require different starting materials or different reaction conditions and do not arise from this mechanism. The strong thermodynamic driving force of aromatization, gaining ~36 kcal-mole resonance energy, makes benzene the overwhelmingly favored product. Therefore, the correct answer is B. Therefore, the correct answer is option B.